It's counterintuitive. You have to press the down button. There you go. Yeah, 2 minutes. Okay, welcome everybody. Welcome to the EECS Department Colloquium. And it's my pleasure today to welcome and introduce Professor Ali Javey. Professor Javey is a very highly regarded and well recognized researcher. First of all, he has his PhD in chemistry from Stanford University. And for a short period of time was a member of the prestigious Harvard Society of Fellows, and he's won a number of prestigious awards, including the Dan Maydan Prize in Nanoscience, MRS Outstanding Young Investigator, Sloan Fellow, Moore Davidow Ventures. Another one, particular interest, he was a member of the MIT Technology Review TR35, best under the age of 35, a few years ago. And he's here, he's done a lot of work on technology and devices, even though he comes from a chemistry background, teaches our course on device physics, and is going to talk to us about some terrific work he's been doing for the last number of years on wearable sweat sensors. Ali.
All right, well, thank you very much. Is the mic on in the back? Can you confirm? All right, perfect. So, so let me start by first thanking Jeff for the introduction and also inviting me to give this talk. I couldn't say no. When you're local, you can't hide. And I gave a colloquium talk 17 and a half years ago in this room, and that was my job talk for Berkeley EECS. And it was in this room 17 and a half years ago. And the talk was on a very different topic. It was about nanoscale transistors and using emerging semiconductors and all that. And today's talk is going to be very different. It's the materials are very different. The devices are very different. The science is very different. But there is a commonality. I remember when I was giving a talk 17 and a half years ago, I was extremely nervous and I was sweating. And it took me 17 and a half years to figure out how I can make that into a practical device. So today I will share with you what we have done over the past, not 17 and a half, but the past several years on developing sweat sensors. This is just one technology that we are looking at. This is one project that we are looking at in our group. Our group is pretty diverse. We have work on transistors, on optoelectronics, and on sensors. And on sensors, one particular sensor technology is wearable sensors. All right. So let me start by first acknowledging these guys, the students and postdocs, and the names that you see on the left. These are the students and postdocs and undergrads, both past and present, that have contributed to sweat sensors. So I'm going to talk about their work. And the ones that are highlighted in bold, they had probably the most amount of contribution. Graduate students on top, postdocs, visitors and undergrads. Quite a few of them have gone to now create their own labs. Yilin, Jerry, Yuanjing, Wei, Jiangqi, they're all professors now, and many of our undergrads that are listed at the bottom, they have gone to be PhD students now at our peer institutions. And our collaborators, I have very close collaboration with a number of groups. I'm just highlighting a few of the collaborators. We have a much larger network of collaborators, and specifically you will hear our collaboration with VTT throughout the presentation. All right, so let me, with that, let me start talking about human sweat and why we are interested to make wearable devices for sweat sensing. First of all, it's readily accessible. I mean, it's the most accessible biofluid. You all know this, you can readily sweat. And in fact, the most...
Doing that right now?
You're doing it right now as well, yes. And under extreme conditions, in fact, you can lose up to 14 liters of liquid a day. And I mean, that's under extreme conditions. I mean, that's really an astonishing amount of liquid that you can lose. You're always sweating. That's the mechanism by which the body regulates itself and regulates the temperature. As you're sitting here, you are sweating, even if you don't feel it. The sweat rate often tends to be very low. So the evaporation takes place quickly and you don't notice it. But of course, if you're sweating a lot, you do notice it. So part of our technology is to capture that very small sweat as you sit around. As you sit around, for example, in a room like this, you are sweating. And we can capture that sweat, we can analyze it, and we can get different information out of it. That's the objective of this project. Now, the first mention of sweat in the medical context goes back to the year 1606. This is the reference. And of course, that's well before modern medicine as we know it today. And basically, there was a myth back in the old days that if you leak the skin of a baby and it's too salty, the baby dies young. And that's what is in that medical textbook of the time. And today we believe, the clinicians believe that reference was to cystic fibrosis. So it actually was not a myth. Cystic fibrosis, which I will talk about, is a clinical condition, genetic disorder, a disease where the patients do unfortunately die young. And the gold standard for detecting cystic fibrosis is sweat analysis. If it's too salty, if the ion concentration, chloride ion concentration is too high, that's how they diagnose cystic fibrosis. Over the years, there have been many applications for sweat analysis, and typically the sweat analysis tests that are done today are done off-body, so they collect the sample from the body and then they analyze it using, for example, conventional labs. And I mentioned cystic fibrosis. The gold standard for detecting cystic fibrosis has been for the past few decades, sweat analysis. For fitness monitoring, monitoring how much fluid loss you have had as you undergo extensive periods of exercise, that's really important. And that is being used by actually even some sport teams. Doping control, drug analysis has been used of sweat in the past for doping control. Many drugs do show up in sweat almost immediately, and it's non-invasive. You can just collect the sample immediately and send it out to a lab, among other applications. Now, again, all of these are done off body, so you get a single point during the measurements. So what we want to do is to do sweat analysis on body, developing a wearable platform. There are many commercial wearables today. In fact, that is one of the fastest growing consumer electronics today. Smartwatch is rapidly growing. The market size is rapidly growing. It's exponentially growing, in fact. And there are many sensors that are incorporated in the commercial smartwatches today. If you buy a watch, it has all sorts of sensors that can measure your pulse. You can measure your activity rate. You can now measure also your skin temperature. That's the newest introduction of a sensor. But these are all physical sensors. And what we want to do is add chemical sensing, so be able to do sensing at the molecular level. And for that, we are interested to look at sweat, because that's really the only non-invasive way that you can continuously monitor the body. Interstitial fluid is invasive. You have to put a needle. Blood, of course, you have to implant. And here, the objective is to do it non-invasively for sweat, just on the skin. And the applications that we're looking at are both for fitness tracking, so monitoring athletes, and also for diagnostic and health monitoring applications. Now, the two type of devices for these two cases are actually very, very different, and I will talk about them. Here you have subjects that are sweating quite a lot. They are biking for extensive period of time, and you have a lot of sweat samples to deal with that you can collect and analyze on body continuously. For medical applications, you don't want to get a subject to bike for you. So here, the objective is really to study sweat analysis, to do sweat analysis at very low sample volumes. So you're dealing with very low sweat rates and capture that small amount of sweat, which is on the order of tens of nanoliters or hundreds of nanoliters, and analyze that. And the eventual goal for us is to move towards big data. If you can imagine, if you can continuously monitor different biomarkers over time, we don't have that ability today except for glucose. There are glucose continuous interstitial fluid sensors that you can put on the body. They're invasive and they measure the glucose level. But beyond that, we don't have the ability to continuously measure any biomarker. You do blood analysis, those are discrete points. You really don't know how the different biomarkers are dynamically changing over time, and we think that would really enable us to look at personalized medication and personalized treatment in a new way if you know where is the subject's baseline and look at the deviations from that. Now, as we started looking at doing on-body sweat sensing, we ran into a lot of problems, and here are just a few of the challenges that we overcame and we had to deal with, and some of them we're still tackling. And this has started with just one or two bullet points, and over the years it kept growing, and still I'm sure this is going to continue to grow as the new generation of students and postdocs continue to work on this direction. First of all, you're dealing with often low sweat rates, small sample volumes, and low concentration of analytes. And if you're trying to measure analytes in analytical chemistry, what we teach the students is if the sample volume is low, if the concentration is low, you're in trouble. That really hurts your accuracy. And we're trying to do that on body. So the challenges that come about from making reliable sensors that can analyze those small amount of samples is quite this is a quite challenging problem. Contamination from skin. If you're trying to measure glucose and the subject had used moisturizing soap. Moisturizing soaps do have sugars in them. The surface of the skin is contaminated. Then what are you measuring? So we have to make sure that, of course, the skin is contaminant free. And so for each of these, we came up with different protocols, and we also designed the device in certain ways to address these various problems. Now, there have been a lot of work done by the community as a whole, looking at different types of wearable sweat analyzers, and certainly we are not the only group. There's a lot of beautiful work and important work done at Cincinnati, at San Diego, at UIUC, and now Northwestern by various groups, just to name a few. And everybody is looking at more or less a different platform, a different approach, and really that has enabled the field to move forward pretty quickly. And so let me, for the purpose of the talk, focus on our own work and our own technology. This is the very first device that we developed. We published this back in 2016, so 6 years ago now. And from early on, we took a systems approach for doing sweat analysis on body. So we actually not only built the transducers, the chemical sensors, but we integrated them with silicon ICs to do signal conditioning, to do signal processing, and data transmission. So here, the device, as you look at it, has two components. There is a disposable component in this case, where you have your chemical sensors, those are your transducers. Then you have an electronic board, and this is where you do signal conditioning and data transmission, and eventually it goes to a phone. Now, over the years, we have developed all sorts of sensors for different analytes. We can measure different metabolites like glucose, lactate, different ions, heavy metals. Heavy metals are quite interesting. If you get exposed to heavy metals, right away they actually show up in your sweat. The body tries to get rid of them immediately through sweating and urination. So you can pick them up immediately in sweat and urine before it shows up in blood. And so you can actually measure immediate exposure of heavy metals. Drugs, many drugs do show up in sweat. We have measured a bunch of them. A few of them are listed here. Vitamins do show up, and their concentrations are shown to be correlated with the intake. We have shown that in our own lab. And our device also has a skin temperature. We had skin temperature on our devices back in 2016, and this is well before Apple finally introduced a skin temperature sensor on their device this year. And finally, sweat rate. Now, of all of these, if you ask me which one is going to be introduced next, so skin temperature is already gone, that's already introduced. At least the Apple Watch has it. I believe sweat rate sensing is going to be the next sensor. So you will see, in my opinion, that my projection, sweat rate sensors within the next 5 years. And I think the technology is already mature enough that can be adopted within a commercial wearable device. All right. So what I'm going to do for this talk is I'm going to spend the first half talking about our device, the technology, and our toolbox, how we develop different components. And then the final half is going to be subject studies. What have we learned from doing sweat analysis? So let me start by the technology. So I mentioned that there are two components to the device. There is the disposable part that is made on a plastic substrate that you put on the skin. That's the part that is in intimate contact with the skin. That's the part that is doing measurement of the different biomarkers. And we use different modalities of sensing. You can use electrical sensors, optical sensors, electrochemical sensors. For the purpose of today's talk, I'm going to focus primarily on electrochemical sensing, but you can use other sensing modalities as well. And I will just give you a few examples of these electrochemical sensors. For the case of metabolites like glucose and lactate, typically what we make are enzymatic sensors. And the sensor is as follows. There's an electrode that we fabricate on a plastic substrate that sits on the skin. And there's an enzyme layer on this electrode. And when glucose arrives, there's a chemical reaction, and that gives you current. So in this case, you're measuring current, and the current is correlated to the concentration. And so you're measuring this electron that is released as part of the process, and the number of electrons that you get is correlated with the number of glucose molecules that you have, or lactate molecules that you have. So in this case, we're measuring current. We can also make sensors where we measure voltage, where the signal is voltage. And as an example, we make ion selective sensors. And in this case, these are primarily the sensors that we use for sodium, potassium, pH sensing. And here, the device is actually quite simple. You have, again, an electrode, a metal electrode, and on top of it, you put down a material that is called iontopore. And these are commercially available materials. And these iontopores are these basically porous molecular membranes that allow certain ions to selectively pass through. So you can buy them for potassium selectively or for sodium selectively. And the end result is voltage. You get charge on the surface, and that gives you, the signal is voltage. And the voltage that you get, in electrochemistry we use E versus V. So this is the voltage that is measured, goes as 0.06 volt per log concentration of analyte. So 0.06, that's 60 millivolt. So it's 60 millivolt per decade change in analyte concentration. And in fact, I think yesterday I was teaching my class 60 millivolt per decade is a magical number in our device technologies, of course, in our solid-state devices. For a diode, ideal diode, the slope is 60 millivolt per decade. Ideal transistor, the slope is 60 millivolt per decade. And for an ideal ion selective sensor, based on the Nernst equation, the response is also 60 millivolt per decade. They're all the same equation. The underlying physics is the same. It's the same equation. We give them different names depending on whether you're dealing with ions or electrons. And so the reason for the 60 millivolt per decade at room temperature is the same. We can also measure heavy metals, and let me just give an example of how we do that for the case of heavy metals. It's, again, a very simple device. You just have a substrate, a plastic substrate. You pad on your electrode. And then in this case, the electrode is either gold or bismuth. You first electrochemically deposit your heavy metals on the surface of the electrode, and then you use anodic stripping voltammetry to remove these analytes, these heavy metals, from the surface of the electrode. And as you do that, you get these peaks as a function of voltage, and each peak corresponds to a different heavy metal. And by using either bismuth or gold, you can actually target the different heavy metals. Again, this is a well-established sensing modality, but what we have done is now transfer it to plastic substrates and try to make these reliable and mass-producible, as I will talk about a little bit later. Sweat rate is particularly interesting. I mean, it's something that I mentioned to you that I was sweating when I was giving a talk 17 and a half years ago, quite a bit. When you're under stress, you sweat a lot. And as I will present to you a little bit later, you can actually monitor the stress level of a subject by looking at their sweating. Of course, you have to look at the activity rate as well, so that you have to do a multimodal sensing, and you can actually get information about the stress level of the subject. So how do we do sweat rate sensing? We have different, again, approaches, but the one that we have primarily focused on over the years is to use microfluidics. So in the case of microfluidics, we basically have tiny tubes, tiny channels that the liquid can go through, and we have an inlet for this tube, for this microfluidic. The inlet is the collection area that sits on the skin that covers multiple sweat glands. Sweat goes through the collection area, it goes through the tube, and along the length of the tube, we can put electrodes, and we can basically monitor where the fluid is. So we have different strategies for that, but you do basically impedance-based sensing. and you know exactly where your fluid front is, and from that you can get your sweat rate. And we can put our electrochemical sensors also within this channel, within this microfluidic. So now we have a microfluidic that is sitting on the skin with the integrated sensors. Over the years, we have also looked at the form factor. That's really, really important, the packaging, the form factor. How's the device going to look like? So we have played around with different ideas. One idea would be to make a standalone device. So rather than grabbing a watch or a Fitbit, smartwatch or a Fitbit, and modifying that, let's just make our own new device. And so that's one possibility. And in this case, we basically have a device with a display, and this is a very simple device. In this case, we're measuring glucose concentration on the surface of the skin, and the display puts out signal that says either it's the low, medium, or high, the glucose level concentration. We get the actual value, but in this case, we chose to plot it like this, to display it like this, because first of all, if you do it like that, then it's not a medical device. If you just simply say low, medium, high, it's not a medical device. It's a consumer electronic device. So the regulations actually will be a little bit different, and your accuracy also can be a little bit off, and you still give the information that is needed, related information that is needed to the subjects. Now we went a little bit further than that, and we thought about how we can power this device. You know, I'm surprised that. Well, there are some bands that the watch band is a great place to put a photovoltaic cell. And you know, one of the problems with these smart watches is that you really have to charge them every day or every 2 days at best, and that's really annoying. I used to wear them all the time, the watch, several years ago, and I just gave up. I just gave up from charging the watch. And you can simply put a flexible photovoltaic cell. This is a commercial photovoltaic cell, and put it as part of the band. And the power that you get from this is sufficient to charge the battery to the degree that it will minimize your charging. And I'm surprised that this is not becoming a standard form factor for the wearables today, but that possibility exists. Many calculators, of course, have that, and you can imagine that your watch could also have it. You can make them look fancier a little bit. You know, you have those chain bands, for example, the metal chain bands, and you can have these strips on each, for example, metal piece, right? So you can make it look fancy, and I'm surprised it has not been adopted widely yet, but that technology exists. Now there is a second approach for the form factor, and that approach would be, let's grab an existing wearable device, for example, a smart watch, and in this case, the user, the user is sitting right here behind in the third row, and the user is wearing a smart watch, and they integrated the sweat sensing platform as part of the band of the watch. So now in this case, you're not designing a new device. You're grabbing an existing device and you're just adding a sensor to it. And I think from commercial point of view, this may be more viable. I mean, rather than introducing a completely new device, you can start to think about integration. Now in this case, we're not showing it, but there are wires that are coming out, and then we have another watch-like device that sits on the arm, and that's where the electronics are. But you can imagine that the band would have the wires, so the signal is directly sent from your sensors to the watch, right? So that can be done. And now this is an interesting device. In this case, we don't use any adhesive to connect the sweat sensors, the microfluidics, onto the skin. We simply, by properly engineering the dimensions of the device and the shape and the size, there's a collection well here, we can deform the skin just enough to form a seal, and that seal is good enough to prevent leakage, and we collect sweat. The sweat is then sent through the microfluidic, and you can see there are a bunch of electrodes along the length of the microfluidic, and that's how we can measure sweat rate. So we think that this is an easy way to do sweat measurements. And again, I think the most important information you can get from sweat right now that I'm confident about is sweat rate. That's the easiest device that I believe will be integrated next. So what can you get from all these different platforms and all these different form factors? This is just one example set of data. This is from our first work. But this is the idea. That's why the title of the talk is Towards Big Data. We're still not at the big data stage, but this is the set of data that you can get. You can have your physical sensors giving you heart rate, VO2, VE. Then you can have the skin temperature. This is our own skin temperature sensor. Measure lactate, glucose, sodium, potassium, and again, sweat rate. At that point, we didn't have a sweat rate sensor, but you can start to get a lot of data continuously as the subject, in this case, undergoes exercise. For example, a bike exercise. In this case, the subject was biking, and the top panel shows the biking power. So that's the objective. And then the question, of course, is what information can you extract, which I will start to share with you in the latter part of the talk. Now, so far, everything that I've presented to you is for devices where the subject is sweating quite a bit. And for example, when the subject is running or biking or exercising. And we can measure the sweat rate. We can continuously measure the different analyte, push the old sweat to the microfluidic channel, continuously measure the fresh sweat. But what if we want to start to use this device for medical applications where we cannot get the subject to bike for us for extended period of time? So for that, it's really important to be able to do at-rest measurements, so be able to do sweat analysis when the subject is at rest. For that, we have looked at different platforms over the years, and the very first platform that we looked at, that we published in 2017, is that the device, within the device, there are two pairs of electrodes, these electrodes that are in the outer part of the device, and we coat one of the electrodes with a drug. The drug is FDA approved, and this is the same drug that is used for collecting sweat for cystic fibrosis subjects, including from infants. And what happens during this process, which is called iontophoresis, you basically pass current between the two electrodes and you push this drug into the skin. And there are many drugs, actually. This is just one of them that is listed here. There are different drugs that you can use. And these drugs locally activate the sweat gland, and you get local sweating. And so the device generates local sweating, and then you can put the sensors in the middle. Now, in this case, we didn't have the microfluidic, but of course, you can put the microfluidic in the middle, and you can then continuously do sweat analysis. Now, the problem with iontophoresis is you have to use a drug. Granted, it's FDA approved, but we were trying to work with cardiologists at UCSF, and there was some concern as to, for example, can we use it on subjects that have had that have had heart surgery? Can you apply this drug on the subject? And the answer finally was yes, but there's a concern whenever you're using a drug and the subject is, for example, hospitalized for a heart surgery. In that case, there is a concern when you are introducing a new drug into the subject. And but this works. This is a well-proven strategy, and it's already used by clinicians. And the only thing that we have done that is different is that we have integrated this iontophoresis element with the sensing element. So this is one approach. Now, a couple of years ago, we were able to show that you don't need to do iontophoresis to collect at-rest sweat by properly designing our microfluidic device, including the inlet, and by making the dimensions small enough and putting it on parts of the body where the sweat rate is highest, which is your fingertip. That's enough to collect the sweat even at rest. And I thought that this was an important advance because now we can access sweat at rest. We can measure at-rest sweat rate without any drugs. And we can use that, of course, for monitoring not only analytes, but also stress levels potentially. And it worked. The device is a simple device, and it works. And we can put this device on different parts of the body. Here I'm just showing images of the microfluidic, and you can see in this case we use a dye, coloring dye for clarity. And as the sweat enters the channel, you see this green line. So the green line or the blue line or teal line or whatever color it is, that depicts the sweat entering the channel. And we can put these on different parts of the body. And in this case, we tried them on 8 different parts, and they're labeled. And we can measure the sweat rate at each location at rest. And what you see here is that by far, you get the highest sweat rate on the fingertips, not surprisingly. And you probably have noticed this, that as you're sitting, if you hold your hand tight so that you're not allowing evaporation to take place, your fingers will get wet after a few minutes. And that's sweating, and you can collect that sweat. And the sweat rates are actually relatively high at the fingertip. We do have a subject, one of the students who's wearing one of these sensors, and at the end of the talk you can actually go and take a look, and he's trying it, and we will see how his sweating is coming along. All right. Now the fingertips, of course, are a great place where you can place these sensors, and we went one step further and we said, well, you can put a microfluidic, and that's great for doing continuous measurements, but what if you just want to get one-point measurement? What if you want to measure one analyte, concentration of one analyte at one point? For example, see if the subject has taken a particular drug or not. And what's the easiest way to collect sweat for that case? And the answer is just wear gloves. Use a glove-based device. And for those of you who work in labs, experimental labs, you know if you wear gloves for some time in the lab, when you take off the gloves, and these are just nitrile gloves, the gloves are wet. That's all sweat. And it can be quite wet, in fact. And so the students figured out a way to, in fact, even fabricate the sensors directly. And in this case, this particular sensor had both chloride ion, pH, and ethanol sensing capability built onto the surface of the glove. And or you can do it even with the finger cots. So the finger cots would be, these are just commercially available, just covering one finger, so you don't have to cover the entire hand. All right. So far I've talked about the technology and different form factors and different components. I'm going to now focus on manufacturing. How do we mass produce these sensors if we want to do subject studies reliably? And for that, we started to collaborate with different groups. One of them being Professor Cho's group, who is now at SKKU. They have gravure roll-to-roll printing infrastructure. And so we looked at gravure printing of the electrodes. And so here now you have a sheet, a roll of these electrodes that are printed. And these rolls can be as long as 100 meters. And these are printed extremely fast, just like newspaper printing machines. And you can mass produce these sensors, and then you just have to cut each piece, basically each device. You can cut them. And in this case, there was no microfluidic. But the big question for us was, if you print devices using roll-to-roll printing, would the device variability be high? So we were very concerned about device-to-device variability. And to our surprise, in fact, the variability is actually fairly low, much lower than our lithography evaporation-based devices. And here I'm showing you just the bare electrode. We were using the bare electrode to measure the redox reaction of a well-established redox couple. And these are, I forgot how many devices. I think there are 50 or 100 different devices. The CV curves are overlaid on top of each other, and you can see that the CV characteristics that you get from these different bare electrodes is pretty reproducible. And if you functionalize them, again, you get very tight variations. And just take my word for it. These are published. You can look at the exact specs. And this was done in an academic lab. This is a roll-to-roll printing in an academic lab. So then we moved to VTT, which is a basically it's almost it's a national lab in Finland. It's almost a national lab in Finland, funded by the government of Finland, and they are one step below a manufacturing house. So they're designed to be a facility where you can grab an academic research-based device and start to scale it up. So we started working with them, and now we print, roll-to-roll print, or process, roll-to-roll process, the microfluidic as well as the electrodes and the various sensing layers. And so we get these sheets that again, everything is roll-to-roll process, and you can use these sheets and cut them, and those are your sensors that you can install. All right, so that's the technology side, and for the remainder of the time, the next 5 or 10 minutes, I'm going to show you some case studies that we have done using our sweat sensors. The first one is cystic fibrosis. I already talked about cystic fibrosis. The gold standard for detecting cystic fibrosis is sweat analysis of chloride ion. And as a rule of thumb, if the chloride ion concentration is less than 40 millimolar, CF is unlikely. If it's greater than 60 millimolar, then CF is likely to be diagnosed. Now, this was the gold standard for decades. Today, genetic testing is very cheap. So at this stage, typically, they send the subject to genetic testing. So that's how they do the confirmation of cystic fibrosis. So we went to Stanford Medical School, and we worked with the clinicians there, the Cystic Fibrosis Center at Stanford with Carlos, and we installed sensors on both healthy subjects, basically patients and nurses and ourselves, and also patients. And you can clearly see that in the case of patients, you can measure chloride ion concentrations that are extremely high. In this case, the range was anywhere between 90 to 100 millimolar. So we looked at multiple patients, and in all cases, we were able to correctly detect them or diagnose them. In the case of healthy subjects, on the other hand, it was pretty low. Now, the other interesting effect is that it's known that for cystic fibrosis patients, the chloride ion concentration is higher than sodium. For healthy subjects, it tends to be the other way around, and we were able to also monitor that. So this was a sanity check. This is an application where it's known for sweat sensing to work, where it's the gold standard for detecting a particular disease, and we just wanted to make sure that our sensors are good enough. Again, in the past, they would collect the sweat, they will send it to a lab. It will take a few days to get the results. We could get the results immediately, and the subjects could do the test at home as well. Another interesting trend that we are observing is that by measuring the local sweat rate as the subject, for example, exercises, not surprisingly, you can predict the whole body fluid loss. So, if the subject is exercising severely, that they're losing a lot of fluid, you're worried about dehydration. And one definition of dehydration is if the subject loses 2% body weight by sweating, basically by losing 2% body weight by losing liquid. And so having a device that can measure how much body fluid you're losing, how much body ion you're losing is actually quite informative for athletic applications. And what we see is that by putting the devices on forearm and forehead, we now have a lot more data than this. This was our original work. We can see a correlation. And the correlation is not perfect, is not precise. There is some variability from from subject to subject, but you can still get a correlation that can be quite informative. So again, having that device on a watch could give you information about how much body fluid you're losing as you're exercising over time. Here is an interesting application. In this case, this is a device where the subject is putting the sensor on their skin, on the fingertip. And the subject is not exercising. They're just basically going through their normal activity. And we monitored them for 24 hours. And so this time is, if you convert this minute to hour, this would be 24 hours. And at the bottom, that's the sweat rate. And the subject was basically sitting around, sleeping, walking, Zoom talk. This was during the pandemic. And the Zoom talk in this case was a research talk with the, happened to be with the advisor. And so the subject was stationary. So when you give a Zoom talk or Zoom discussion, you're sitting, you're not moving around, you're not exercising. Now we measured the heart rate, and you can see the heart rate during the Zoom talk went up, but not by a whole lot. I mean, the fluctuations is quite large. This is using just a Fitbit. This is a commercial device. But look at the sweat rate. The sweat rate jumped by 2 orders of magnitude. And that's all stress. That's from being excited to share research results. And one of the students installed the device also prior to an exam. And this was again a Zoom exam. And so they looked at the sweat rate sometime before the exam, during the exam, and then after. And again, during the exam, the sweat rate shot up by 2 orders of magnitude. This was a Zoom exam, sitting stationary. The sweat rate shot up. If you just look at sweat rate by itself, it's not informative because you don't know if you're walking, if the room is hot, if you're running. But if you measure the activity rate, the number of steps that you're taking, the heart rate, and the temperature, if you combine all of them, then of course you can figure out when the subject is getting excited or when the subject is getting, in this case, stressed by just looking at sweat rate. A very, very simple, and this was pretty reliable. We always saw this trend. Another interesting trend and another interesting application for just looking at sweat rate was monitoring a diabetic subject when they underwent hypoglycemia. So this is a condition when the blood glucose drops too low, below the standard level. And so what you're looking at here, this is the interstitial fluid glucose concentration. This is using a commercial device that is FDA approved. Many diabetic patients wear this. Again, this is a device that has a needle that goes in, and you leave it on for a week. And you continuously measure your glucose level. And you can see that as the concentration of glucose went down, the subject was sitting still during the whole time, the sweat rate went up. And this is quite informative because the commercial sensors, these sensors, based on what the clinicians have told us, they don't work well when the glucose concentration is too low. So when the glucose concentration is at the low limit, the sensors actually fail. They do not provide accurate information. So the sensors are not good in the hypoglycemia regime. These are commercial devices that diabetic patients wear. When the glucose concentration is high, they're very informative. They're very accurate. But at low concentration, they're not accurate. And there are a few causes for that, but they're not very accurate in that regime. Well, if you combine that with a sweat rate sensor, then you get the full picture. So again, you can't just look at sweat rate. You have to combine it with other data. And we saw this over basically multiple measurement cycles. All right. The other interesting trend that we see is drugs. Drugs do show up in sweat immediately. When you take a drug, most drugs, not all of them, but most of them, the small molecule drugs, show up in sweat. For some, people have done off-body analysis over the years, and they have shown that the concentration matches that of the blood or matches that of the intake. And so, in principle, you can continuously measure the drug concentration level of a subject. And this is not only useful for doping control, but also could be useful for personalized medication. Different subjects have different metabolism rates of different drugs. And for some drugs, including treatment of cancer, getting the dose just right is critical. The problem is the dose can never be made flat. You're always absorbing the drug, you're burning them, you're metabolizing the drug. So, and the absorption rate, the metabolism rate is different for different subjects, is different at different times. So right now for many conditions, the dose that is given is a bit of a random process. I mean, it's just basically they give you a certain dose and just to see how you respond, and then they adjust it accordingly. But it doesn't account for the fluctuations of these rates, the metabolism and rates of the subject. So for this, we started looking at caffeine. And caffeine, because we're in the electrical engineering department, that was the easiest drug to give to a subject. And the subject, the student was basically drinking coffee. And this was when we could only measure sweat during exercise. This is before we had the at-rest sweat sensors. So the subject had to bike after caffeine intake. Caffeine intake is done at minute 0. So that, of course, messes up the absorption and metabolism rate, right? So if you're exercising versus you're sitting still, your absorption and metabolism rates are going to be very different. But nevertheless, this is what we saw, that the concentration kept going up, and it peaked at about 60 minutes, and then it started to decay over time. And so the peak concentration happens at 60 minutes. So if you need to take your drug, the caffeine, for a critical job talk, take it 60 minutes beforehand. That's basically, that's the message. And we also have done this with other drugs, which I'm not going to talk about because of the time, including levodopa, which is a drug that is used for Parkinson's disease. That's a brain disease. And for anything related to brain, if you're trying to regulate the brain function, getting the dose just right is critical. If the dose is too high, the subject is out. I mean, they cannot function at all. If the dose is too low, it doesn't have an impact. So again, we think that these sensors could be used for such applications. All right, so for that, let me come to my conclusion and outlook slide. So these are some of the key directions that I considered, and these are some of the things that we are looking at in our own lab. So we're continuing to improve large-scale fabrication. If I want to do medium-sized or large-scale population studies, I need a lot of sensors with robust and reliable response. And we are getting closer and closer, but also the packaging is really important. You want to make sure that the packaging is done in such a way that you can collect the sweat properly, you're not getting any leakage, and you're not contaminating your sample as well. So we're putting a lot of effort on that. We still need to do a lot of basic science studies. I told you that I think for sweat rate, that's really the first application that makes the most sense from the product point of view. But for many metabolites and analytes and biomarkers, it's really important to figure out what's the correlation or lack of correlation with the concentration in sweat and blood. We still do not have a good picture for some of them. For drugs, for vitamins, we have a good picture. For glucose, if you ask me, I still do not know what's the correlation, and we are looking at it. I still do not have an answer. And finally, how do we start to incorporate our devices with commercial wearables? And are we close to that? And again, I think the answer is yes for sweat rate. And so with that, thank you very much, and I will take any questions that you may have. Thank you.
Thanks very much, Ali, for a very sweaty talk. Okay, do we have any questions? Please use the microphone since we are recording. I think, Greg, you had your hand up first.
Great talk, Ali. I was wondering, why do you say only sweat rate is close to commercialization? What prevents other multiple metabolites simultaneously being read out by smartwatches or your bracelets?
Really good question. So there are so many challenges that I didn't talk about that we keep focusing in our own lab. So drift, the signal drift. You have a sensor, the sensor should have minimal drift. The signal drift of a sensor gives you error, your accuracy. So we need to have pretty small drift if we want to continuously measure for an extended period of time. So that's the work that one of our postdocs has been looking at for the past 2 years for just one sensor technology, minimize the drift. The second aspect is the sensor-to-sensor variation has to be very small. Otherwise, you have to do calibration of each sensor beforehand. So the question is, can we start to move away from that? Can we get rid of calibration? That's really challenging for any sensor technology. Typically, when you make a sensor, you package it, you calibrate it, and then you sell it. And do we need to do that for all of our sensors? Do we need to do, and if we do calibration now, would it change a week later or a month later, right? There are challenges there. And then you want to make sure that the sensor doesn't die off after X number of hours. So those are the challenges that we are looking at. But also, we need to make sure that the information is there. You know, you can't just commercialize a sensor when you're not sure what information you're going to get out of it, right? The temperature sensor was finally integrated with Apple Watch just recently. And this was after it became clear that they can predict certain information from it. And the information that they can predict is ovulation cycle. And they read the data at night when the subject is sleeping. They look at the skin temperature at night, because you can imagine if you're moving around, your skin temperature is all over the place. So just monitor it at night, right? And they can predict ovulation cycle. To what accuracy we will see, because now you're going to get much more data. But before you commercialize a sensor, you really need to know what information you can get. You can't just say, here's a sensor, you play with it, you guys figure out what you can get out of it, right? That's one way to do it, but that usually fails. So that's where we are.
Okay.
Thank you.
Great talk, Ali. So you explained the challenge of measurement with a small amount of sweat. So is that due to limitation of the sensors, or is that due to the fact that it's changing all over the place when you move?
Yeah. So let me give you one example challenge. So first of all, the concentrations are very low, so the sensors have to be very sensitive. And if the concentration is low, the signal is low, and you have any drift, your tolerance of drift then becomes really low. So you have to have a very robust sensor in that sense. So that's one challenge. Another challenge is if you're trying to do dynamic concentration measurements. So for example, if I want to see how glucose is changing with time, if I take food and the sweat rate is low, well, I need to get rid of the old sweat, right, to be able to analyze continuously the fresh sweat. So for that, our solution is let's push the old sweat into the microfluidics. We have a microfluidic. But if the sweat rate is low, and you can calculate, there is going to be a decent amount of back diffusion. So you have to calibrate the signal according to the sweat rate, and that gives you then what's the lag time and what's the effect of the diffusion. So it's actually pretty complicated to deconvolute that. Sweat rate is pretty straightforward. Sweat rate you don't have to deconvolute. But when you're doing analyte concentration measurements, there are a lot of challenges. And in our lab, we have one of our postdocs sitting in the back. He has spent the last year and a half just looking at one sensor. How do you reduce the drift of that sensor? And that's critical in the field, right? I didn't put any new sensors here, and in fact, in my lab, we ban looking at new biomarkers. We can make sensors for every biomarker, and you can do a few subject studies. But beyond that, it's extremely challenging, right? And so we're saying no more new biomarkers. Grab the existing biomarkers and really make the sensors functional. And that's the challenge.
So a general question that I also have is, so what can be measured from the sweat? So what are the limitations? So monitoring the health there are many things that can be looked at.
Yeah, so it's a most accessible biofluid, right? So right now, the standard biofluid that is used for testing is blood, and that's the key test that you do if you go to a lab, you go to a hospital. That's the first thing they do, right? And so the question is then, they do a chemistry panel. They look at ions. That's usually the first test. So the question that we have is, how about if we just do sweat ion? Is that correlated with blood ion? So we have a project on that, right? That is at a exploratory stage. And so if that's the case, that's great. You don't have to go to a hospital to measure your ions. You can do it at home, right? And non-invasively. And you can just get 1 point. You don't need to continuously monitor for something like that. You get a 1 point, so you can use some of the 1 point measurement techniques. So that's just one example. But you can imagine eventually being able to complement the blood testing with at-home testing for sweat, but more importantly, look at the dynamic changes, which you cannot get from blood.
Okay.
Sorry.
Question over here.
Controlling that.
Hi. I really enjoyed your talk, by the way. I noticed that the slides on the manufacturability was restricted to the patterning of the electrodes as well as the microfluidics. I was wondering what your thoughts were on the manufacturability of the sensing membranes for your multi-sensing arrays, as well as the functionalization, the enzyme functionalizations, and how you think that might be integrated with the roll-to-roll.
Yeah, really good question, and the answer will come out very shortly, I think, for that. So we'll have an answer for that soon, hopefully in a few months.
Okay,
And
last
so
question.
That's we're very close to getting that address as well. Yeah.
The last question is back over here.
There's one more question that has been, I think, maybe.
No,
Okay,
I've
got
been
it.
watching. I think he was first.
Got it.
Either one. Okay, in that case, I'm going to piggyback off of Bobakar's question a little bit longer. During your talk, you said that you currently put your sensor on a fingertip in order to get a sufficiently high sweat rate that you can measure it with your device. And you just now answered that, yes, the sense rate for really low sweat rates is one of your major limitations, and drift might be part of that. My question is, how many more orders of magnitude would your sensor be to sense the theoretical maximum amount of information from a very low sweat rate? And what new technologies do you think you will need to hit it?
Yeah, really good question. And okay, so let me tell you how we actually do the sweat rate sensing right now. There is a microfluidic, and we have electrodes crossing the microfluidic at certain interval, certain spacing, right? And the size of the microfluidic, the cross-sectional area, dictates then basically your sensitivity to the sweat rate. The smaller it is, the better. The problem is if you make it really small, then you cannot make the channel long because the resistance for the flow will be too high. So there's some fundamental limitations in designing the size of the channel. But in general, the smaller it is, the lower the cross-sectional area, the smaller cross-sectional area it is, the lower the sweat rate you can measure, right? Are we limited to only microfluidics for sensing of sweat rate? And the answer is no. We are looking at other approaches as well in our lab, which could, in principle, be applicable to perhaps lower sweat rates as well. And that, I tried to focus mainly on published work, and that's something that our current generation of students and postdocs sitting in the room are actually looking at.
Okay, one more, and then we'll break.
I'm just wondering if you have interspecies drift, or do they all drift at the same amount? Because if you could just normalize by the total, adding all the species.
Yeah, so really good point. So the drift of the signal of the sensor, all sensors drift, and this is the drift in the signal of the sensor, can in principle be corrected for. And in fact, there are commercial glucose continuous monitoring devices. These are the interstitial fluid ones that are invasive. And they are FDA approved for 7 days using basically the same exact sensing modality that I presented. Granted, it's for 10x higher concentrations because they're measuring interstitial fluid, which is the concentration is 10x higher. But those are FDA approved for 7 days. We have talked with clinicians, and clinicians tell us that you can trust the data for up to 30 days. The 7 days is actually not a limitation of the sensor. The worry is you have something poking into your skin and the complexity that could arise from infection if the area is not kept clean. So the sensors can work for that long. That sensing modality can work for that long, for 7 days, and according to some, up to 30 days at least. And the first generation of these commercial sensors that diabetic patients use required 2-point calibration per day. The subjects had to do a finger stick test. They basically had to get a droplet of blood and get the concentration of the glucose from that droplet, put it into the device, and the device would calibrate itself based on that. You had to do it every 12 hours. Today's generation of these commercial devices do not require any calibration, even when you receive the device, and they're calibration free for 7 days. There is no calibration. And the way they did it is not because the sensors have zero drift. No, they have a lot of data now. They have millions of data sets. And they know exactly by how much the drift takes place. And they feel so confident that they can predict the drift and they can calibrate for it. So it's signal processing. The device automatically calibrates for the drift. Now, can we do the same thing? Yes, but we are far away from that because we don't have that many data sets to.
Does one drift more with respect to the other? I mean, if they all drift to the same amount.
Well, each sensor, each analyte sensor would have a different magnitude of drift. Each right? So glucose would have a certain amount of drift. The sodium would have a different amount of drift, and you can, in principle, calibrate each individually. Yeah.
Okay, I think maybe we should stop here. And maybe Ali will stick around if you want to talk.
Oh, I should make an announcement. We actually did bring some sample devices. So if you want to take a look at some of the devices live, we didn't bring the electronics, just the sensing part components. You can go in the front row, and he's to Louis. Louis is sitting up in the front. You can see some of the devices in person.
Okay, well, thank you, and let's thank Ali
Thank you.
for a really wonderful talk.
Thank you.
Thanks.
There's a class